Hello! Today we're going to go over section 3.5, which it talks about rational functions. We have here the definition of a rational function. Essentially, a rational function is the quotient of two polynomials as long as the denominator does not equal 0. But we can read it right here. Let p of x and q of x be polynomials where q of x cannot equal 0. Okay, it's very faint, but that is a does not equal 0 because we're not allowed to divide by 0. A function of f is defined by f of x equals p of x divided by q of x is called a rational function. These graphs usually have a vertical or horizontal asymptote, which is a dashed line on the graph that shows that the function will approach that line, but it will not ever touch it. Okay, so it gets really close, but it won't ever touch that line.
So here we have two examples of some basic rational functions. The first one is f of x equals 1 over x squared. That's right here. And you can see I'm going to dash the lines and the asymptotes in red. This function will get really close to x equals 0, but will never touch. It will also get really close to y equals 0, but it will never touch. So this actually has a vertical and a horizontal asymptote. So here we have the function f of x equals 1 over x squared. And again, we have a vertical asymptote here, and we have a horizontal asymptote here. Okay. So if we were to take the parent function, which was for this one, f of x equals 1 over x. Okay, and we're going to transform that. Now, this is going way back to the first stuff that we did this semester, so it's a good review. We're going to look for the horizontal shifts. Then we're going to look for any reflections and horizontal stretches or shrinks, and then we're going to look for any vertical shifts. So first we have right here x plus 2. So that plus 2 right here tells us we're going to move left 2. So we're going to take that parent function that we just saw and we're going to shift it left 2. And then we have this vertical shift of down 1. So what ends up happening though is that not only the points on the function will shift, but also our asymptotes. So what we might want to do first is shift our asymptote. So our vertical asymptote is actually going to shift. I just found more colors. Is going to shift, sorry, excited, is going to shift from being at 0 or being the y-axis, and it's going to shift over to the left. And our horizontal asymptote, which was at the x-axis, gets shifted down 1. Okay, and then we have that point that was at 1. So this is going to shift over left 2 and down 1. So that's going to be right here. And then we had -1. That's going to shift left 2. Sorry, -1. We're just going to shift left 2 down 1. So we get these kind of anchor points. And then we know, okay, well, this is going to come really close but never touch. And really close but never touch. This is going to come really close but never touch. Really close but never touch. Boom. Okay, so that is our shift there. Now, on this one, we have our parent function is 1 over x squared, which we saw above or before, I guess. And then we have a vertical flip or reflection, and then it gets shifted up 3. So a vertical flip won't change our asymptotes, but the vertical shift up 3 will. So first we're going to do that reflection. So it's going to reflect it over the x-axis. So I'm going to graph what just -1 over x squared will look like in purple. Like that. Sorry, it's not a perfect drawing. But then we also have to shift it plus 3, up 3. So I'm going to take that in each of these points, we're going to shift up 3. Which means my asymptote, which is at my horizontal asymptote, which is at x equals 0, actually gets shifted up 3 as well. So that's my asymptote. We also still have our asymptote over the y-axis, So here I'm going to graph my final graph of this in black. This has been shifted, reflected, and shifted. Okay, that was a fun little review. Okay, so now we're going to take a look at how to actually determine and identify vertical asymptotes in a rational function. So we see right here, it tells us that after possibly simplifying the function through factoring, we set the bottom equal to 0. So what that means is that in the original parent function, let's look at that f of x equals 1 over x again. Okay, I'm going to set the denominator equal to 0, x equals 0, we get that asymptote. How cool is that first? Oh, that's scary looking. Okay. So for each of these, we're going to identify the vertical asymptotes if there are any. Now, one thing to note here, and this is kind of weird, and we won't really go much into this, but I want to make sure you know this for your homework purposes. When it says after possibly simplifying the function through factoring. So that means if I factor the denominator and something can cancel with the numerator, that gives us something that's called a whole. Okay, so if it can be simplified and one of the factors in the denominator cancels out with the numerator, we get what's called a whole. So let's look at the examples below and determine if there are any vertical asymptotes. So first thing I'm going to do is I'm going to take the denominator in this first one, x squared minus 4x minus 5. I'm going to factor it. So I'm looking for two things that multiply to get negative 5 and add to get negative 4. Hopefully this is a nice and simple one for us, and we get x minus 5x plus 1. Okay, if I multiply that out, I would get this trinomial. So looking at this, neither of these factors will cancel with x minus 3. So nothing will cancel out. Therefore, there is no whole on this one. Okay, and then we just take these and set them equal to 0 to find out where our asymptotes will be. So our asymptotes are going to be at x equals 5 and x equals negative 1. I just took this term, or this factor, sorry, set it equal to 0, and then I took this factor and set it equal to 0 and solved for x. Okay, so now we're going to do the same thing on this polynomial, the second one, number 3. I keep saying this like you guys can see me pointing at it. So here, my denominator is x squared minus 2x minus 3. So when I factor that, I get x minus 3, x plus 1. Okay, so do you see how this matches the numerator that would cancel out? Okay, so therefore there is a whole at x equals 3. Okay, so we have that whole. Now, all I got to do to find my asymptote is take the remaining factor, x plus 1, set it equal to 0, and then get that. We have a vertical asymptote at x equals negative 1. So I'm going to label these as vert asymptote. Okay, vert right there. Awesome. Okay, so this last example, example 4, we have f of x equals -8 over x squared plus 25. When I take the denominator, x squared plus 25, and set it equal to 0, I can't factor this out. I'll get imaginary numbers, right? We've seen this before. We saw this in 3.4. If I solve this for x, I get x squared equals -25. So x equals the plus or minus square root of -25, which is an imaginary number, which means that this can never actually equal 0. So it can't. Denominator can't equal 0. So no vertical asymptote. Cool. So those are our ways to find a vertical asymptote. We just take the denominator, factor it out, see if anything cancels with simplifying the numerators and denominators, and then determine the vertical asymptotes by setting those factors equal to 0.